interested in providing security. When you have the product of two primes, finding back the two prime numbers that make the product is very hard. And this particular problem is called as prime factorization, and finding an algorithm which does it fast is one of the unsolved problems of computer science. So RSA algorithm, in order to play around with this to provide security, that is encryption, decryption, and public key generation and the private key generation, we have to carry out three types of operations. One is the public key. Already I have mentioned there is a common function f using a public key k is being used, and plain text on that one the encryption has been carried out, and we are going to get the ciphertext, and which passes to insecure channel and reaches the decryption side, that is send receiver side, and then by making use of private key we are going to convert the ciphertext into plain text and make the sense out of it. However, what is this nature of f, k, public and plain text? What are the characteristics? What are the type of operation we are going to do it in this encryption? In the same way, how we are going to carry out the reverse to recover the original plain text, that is ciphertext to plain text, and get it back by making use of the function g, which uses k private and the ciphertext which arrives. And what is the nature of this function g? Is it simple like substitution or transposition, or is it using some polynomial equation or exponential functionality? That makes the difference. So what are we going to use there? We shall see it here. The entire RSA, it is making use of complexity of operations. The operations which RSA is using in key generation, encryption and decryption, they are very complex in nature. If you look at it here, if you want to arrive at the ciphertext, first there will be a plain text. Plain text has been split into blocks M1, M2, M3, M4 up to Mi. And then we are supplying these blocks as the input encryption. To convert the particular block Mi into ciphertext Ci, we make use of the functionality. If you look at here, to convert this, we are making use of, for the message, for the block of the message Mi, we are making use of the encryption algorithm and mod n. After that, it is getting transmitted. To recover original the block Mi, we are carrying out the ciphertext I raised to decryption and mod n operation we carry out. In between, if somebody is trying out to hack it, they may be using the different types of methods. Because of the complexities of prime numbers that are being used in encryption and decryption, recovery is not so easy. It is of exponential complexity. Now in RSA procedure, how we carry out this activity? RSA uses modular exponentiation for encryption and decryption. To attack it, the Eve or the hacker needs to calculate the square root of Ci in encryption algorithm and mod n. Now if you look at it, when you carry out the encryption on the input message block mi, by making use of the encryption, we are going to get the set of remainders Zn, and we are having the addition and multiplication operations. Then after that, when we get this information the other side, that is receiver side, we take this particular set Zn and multiplication and summation operations are part of it, and then we apply the decryption algorithm on the ciphertext CI that has come, and we perform mod n on that to get mi. Here the decryption key which is required, which is a private key, to create it we may make use of two prime numbers p and q. The multiplication of p and q is giving out the value of n, and then we select encryption and decryption algorithm and we carry out z operation, which is having the remainder values that are obtained by carrying out Euler's pi function, Euler's pi n. Then we are having plus and multiplication on that particular functionality which is being used in recovering the original message. Why does this RSA work? We are having so much difficulty. We are seeing that the prime numbers create a lot of complexity, and we are also saying that the recovering is very difficult because of the complexity of factorization, and also performance is pathetic, and having the algorithm which can improve performance and all such complexities are there. Under all these things also, why does RSA work? We are interested in digging the rationale behind the RSA and its operations. Here we want to show that RSA works by showing that reason 1, for any plain text block there is a corresponding unique cipher text block. The type of encryption decryption we use in such a manner that for every plain text block there is a corresponding unique ciphertext. Reason 2 is any plain text is mod of prime number p. P is one prime number which we have used, and the mod of this prime number p is actually give rise to the plain text. Reason 3 is for any plain text with p there is the ciphertext with q. Q is another prime. So plain text with one prime number and ciphertext with another prime number, we are interested in mapping you. Now we shall see reason 1. Any plain text block has a unique cipher text block. Let the ith message block have value mi. Let its corresponding ciphertext be ci. Decrypting the ciphertext using 6.2, which is saying that mi equal to, that is the message block with ith message block that is having value mi, and then corresponding ciphertext message block which is referred to as ci, On this, we are applying the decryption D. When we carry out, we are going to get out of decryption on CI mod n shall actually give rise, it should be as equal to the MI. Now we are showing it now, because ultimately we are providing the security to the message which is being sent and which is being received. But when we are doing this, there should not be any distortion of the message. Message should not lose its meaning out of this encryption and decryption. So what has been sent, what has been received, those should be the same. So we are trying to show it here that the RSA work, when you are doing this encryption on MI and decryption on ciphertext CI and carry out mod n operation on this ciphertext CI, then at that time what value we are getting is allowing us to recover the message which is as same as ith message block with value MI. Now we are taking this right value, the CI ciphertext I that we have received at the receiver side. On that one we are applying the decryption algorithm and mod n operation is there. By using the equation CI is equal to MI encryption then mod n, we are actually putting the value for CI here. When you put that value, then we are going to get MI with encryption mod n raised to d. And now from laws of modulo arithmetic, we arrive that we simplify this, we will get that the message MI is a combination of product of encryption E and decryption D. Now by making use of Euler's formula, when E into D we simplify, we get the ith message block MI raised to 1 plus k into Euler's function n for some integer k. The last step follows from the fact that the D was chosen to be inverse of E modulo Euler's function phi n. So E into D and 1 differ by an integral multiple of phi n. So this is indicating that regardless of the value of plain message block, there is a corresponding ciphertext by performing multiplication of encryption key E and decryption key D, that is E into D and 1 differ by an integral multiple of Euler's phi function of value n. So there is a correspondence between the plain that has been transmitted by carrying out the encryption with the ciphertext CI, which has been converted into plain text by making use of decryption algorithm. When we encrypt plain text, when we decrypt and get back or recover the plain text, when you compare both of them, mathematically we get correspondence mapping. So that has been proved. Because of that, we can say that with all these complexities of the prime numbers, Euler's function, multiplication of encryption and decryption, the integrity of the message that has been and the message which has been recovered by using of decryption algorithm are actually mapped. This is the reason one. Second one is the RSA, it works because any plain text is mod of. To understand this, we require Fermat's little theorem. It plays very important role in number theory and cryptography. Before we try to make the meaning out of the reason 2, first we shall see what is Fermat's little theorem. Once we understand that, then only we will be in a position to understand the reason 2 in a better way. So what this Fermat's little theorem is all about? The Fermat's little theorem plays very important role in number theory and cryptography. It has 2 versions. The first version says that if P is a prime number and A is an integer such that P does not divide A, the prime number and one integer number we are getting, and when we divide that integer number A by P, if we find that the P is not dividing the A, then A raised to P minus 1 is the mod of 1 mod P. Please note here, we are making use of mod. Mod is actually only talking about the remainder. When we carry out the operation of division, we are going to get the value of quotient and remainder. When we are making use of the symbol with the 3 horizontal line, it is indicating that we are interested only in remainder. P does not divide A. If we have to prove that, then the value which you are going to get should not be 0. Means if the remainder is 0, then dividend can be divided by the divisor. So here we want that it should not be. So because of that, we are indicating this. The second version of this is indicating that this removes the condition on A. This is the improvement over version 1. It says that if P is a prime and A is an integer, then A raised to P is A mod P. Means whenever we carry out the division on A and what remainder we are going to get, when you compare with A raised to P, that remainder, then we are getting an a value, the second version removes the condition on A. It says that if P is prime and A is an integer, then the A raised to P, that is A integer value, P is a prime value, A raised to P. This is actually whenever we carry out the division operation on A by P, what value will be remaining? Remainder, as a remainder. So that is equal to AP. Fermat's little theorem is helpful in finding a solution to some exponentiations. So this particular thing we are going to use in proving the reason 2. Any plain text is mod of prime number P. So in this one, we pick up the value of the message block mi. In the reason 1, we have shown that this can be represented as mi 1 plus k into Euler's phi function of n and mod P. P is a primary number. When you carry out, then we have to get the value of mi. So now we pick this value, the mi message value of block I, 1 plus k into Euler's phi n mod P. This can be represented as mi into mi raised to k into pi n. We factorize this and mod P. When we carry out this activity, and then we proceed to simplify, the same thing can be represented as, because of Euler's pi function, we are simplifying it. So how do we represent Euler's pi of numeric value n? If P and Q are two prime numbers, then the Euler's function can be represented like this. So we split phi n, then mi equal to mi raised to k into q minus 1, this whole factor raised to p minus of mod P. Now we shall consider two important aspects here. Suppose GCD of mi comma p equal to 1, that is the message block I comma prime. The GCD of both these number is 1, then GCD of mi raised to k into q minus 1 comma p equal to 1. This is from Little's theorem. Then we simplify this. Mi raised to k into q minus 1, then whole bracket raised to p minus 1 mod p equal to 1. So mi raised to 1 plus k into Euler's phi function n mod p is equal to mi mod p. We shall now look at the second option. On the other hand, suppose that GCD mi comma p, the value of the message I, message block I, that is represented mi comma prime. The GCD of these two values, if it is greater than 1, This implies that mi is an integral multiple of p. In that case, mi raised to 1 plus k into Euler's pi function for n value mod p equal to mi mod p equal to 0. We conclude that regardless of the value of the message mi raised to 1 plus k into Euler's pi function on value n mod p is equal to mi mod p. Means there is a correspondence between the plain text and prime number p by making use of mod operation. What is the conclusion? Any plain text is an integral multiple of some prime number. Now we shall proceed to reason 3. For any plain text p, there is the ciphertext with q. As we have done in the earlier stage, in the similar manner, we can show that regardless of the value of the message mi, because mi is the plain text, there can be m1, m2, m3 like that. The overall plain text we are going to split into blocks, and each block has been referred as m1 or m2, m3 like that. Now, what message we are going to pick up, and if we work out a value for each one of them, what is the value of m1, what is the value of m2, like that. So when we actually obtain the value of any of these messages, regardless of what is the value of the block message that we are arriving at, we can show that mi raised to 1 plus k into Euler's phi n. Please remember the 1 plus k into Euler's pi n. On that one, we are carrying out mod q. So when we do that, then we are going to get the value which is equal to mi into mod q. We simplify it by using the way in which we had done earlier. From equation 6.3, this mi raised to 1 plus k into the Euler's phi n is represented as m1 plus c1p for some integer c1. So mi is the value of the message block, c1 is some integer c1, and p is the prime number. So when we are going to add up to the value of mi, the multiplication of some integer c1 and the prime number p, which is equal to mi raised to 1 plus k into Euler's phi n. Now, by making use of this particular equation, we simplify it further. Mi 1 plus k into Euler's phi n equal to mi plus c2q for some integer c2. Equating the RHS of equation 6.5 and 6.6, then we find that mi plus c1p equal to mi plus c2q. Means when we play around with primary numbers P and Q, when we create the set and map the value of plain text value M1, M2, M3, M4 like that to the corresponding value of reminders, when you map it out, then we can find that the MI value with prime number, then ciphertext value with prime number Q, some other Q, the value, there will be some mapping that will be existing between plain text with the prime value P with the ciphertext with the prime value Q. So if there is no correspondence, then there is no guarantee that what plain text has been transmitted, what we are going to receive, there won't be any correspondence at all. Now we shall proceed. Why does RSA work? Reason 3. For any plain text with P, there is a ciphertext. We continue with that discussion. So, because of this, C1P equal to C2Q. Since P and Q are prime, it follows that C1 should have Q as factor. So, C1P equal to C3 into Q into P for some integer C3. So, substituting this in equation 6.5, we get Mi raised to 1 plus k into Euler's phi function n equal to Mi plus C3 PQ equal to Mi plus C3 n, because multiplication of two numbers P and Q is equal to n, we are replacing it. So, ciphertext value Ci, by making use of decryption, mod n is equal to the plain text block Mi raised to 1 plus k into pi Euler's function pi n. When you do that activity, mod n equal to Mi, means the ciphertext after decryption with mod n operation is equal to the plain text with 1 plus Euler's function phi n mod n operation. So, we are able to recover the plain text from the ciphertext even when the prime numbers and corresponding multiplication is taking place, and we make use of the characteristics of algebra and other related properties to carry out this activity. The conclusion is, regardless of the value of any plain text message with a prime number P, the corresponding ciphertext P should have another prime number Q as a factor. Because when we are interested in mapping the plain text with prime number, from that when we create one set, ciphertext with the prime number Q, we create another set. There should be correspondence between these two sets. That is what we are trying to say here. So, in summary, why this complicated process of RSA, which is involving two keys, one is public key, second one is private or secret key, and which are involving very complicated activities related to the prime number, and decryption activities should work. If we have to show it, then whatever operations we are carrying out by making use of primary number P and primary number Q in encryption and decryption on the plain text and create the ciphertext, and from the ciphertext, by making use of decryption algorithm, when we recover the ciphertext to plain text, when we recover it, then there shall be correspondence. Means even when we perform very complicated activities, then also when we are distorted the original message and convert it into ciphertext, and from the ciphertext, by carrying out very complicated activities of decryption and got back the original plain text, the original plain text that has been transmitted after encryption, the plain text which has been recovered after decryption, there is a correspondence between these two. That has to be ensured. So RSA is ensuring it. Regardless of the value of plain message block, there is a corresponding ciphertext by performing multiplication of encryption key and decryption key D, that is E into D, and 1 differ by an integral multiple of Euler's phi function of value n. Reason 2, we had seen that any plain text is mod of prime number P. So when you make use of the prime number P on plain text, whatever you are carrying out, so it is quite acceptable while converting it, and when we receive it, and we are in a position to recover the original text, regardless of the value of any plain text message, any plain text message with prime number P, the corresponding ciphertext P should have another prime number Q as a factor. So I mean, it seems to be very complicated. In summary, what we want to say is, when we are making use of many mathematical operations and other things which are very complex in nature, ultimately using private key and public key, then also when we are converting the original plain message into ciphertext, and from the ciphertext when we are recovering back the plain text, the message ensure that there is security and the hacker is unable to make any sense. The sender and receiver can make sense, and the message is maintaining its integrity. There won't be any distortion, and there will be one-to-one map between the plain text and the message which we are going to receive at the sender side. That is what we wanted to prove. Because of that only RSA is working properly. Like that we wanted to prove. That was the overall discussion for today. So in brief, the entire operations of RSA is involving polynomial complexity and exponential complexities. It is involving a lot of multiplication and division operations, and because of that the operations become very complex and performance actually degrades. How to ensure that this performance will be improved upon, to ensure that the RSA guarantees the transmission and receive of the message in lesser time without losing the integrity of the message. That is what we shall discuss later. With this, we come to the end of today's discussion, why the RSAs work.